Somebody do me a favor. Keep track of time for the period. If you have anyone have the modified, it's in your email somewhere. Just let me know, because last period I don't think the bell rang to end the period, and we think we went over there. All right, test 3 review. So, first, sections 4.1, 4.2, 4.4. 4.1, 4.2, 4.4. 4.1 and 4.2 we did together, right? 4.1 and 4.2 we did together. That was vectors. 4.4 was horizontally fired projectiles, projectiles fired at an angle. Literally, those two topics are what a 4.4 is all about. We spent a lot more time on the problems where it was fired at an angle because they were a lot more complicated than fired horizontally. I'm going to start by going through a little bit of a brief summary of vectors because that has been a while since we've gone over that, unless you were at office hours maybe. And then we'll go into 4.4 a little bit, and I'll open up the floor for questions you may have on either that exact topic or, something else you want to ask about. What's up?
Supporting this class?
Yeah. Yeah. So the definition of a vector is something that has both a magnitude and an angle and a direction. Very good. And a direction. So a vector itself has a magnitude and a direction. If I tell you that I've walked 5 feet, I'm not giving you a vector quantity because I haven't given you the direction I've walked. I could have walked 5 feet east, south, north, west, 20 degrees southeast, 45 degrees northwest. Any direction changes the vector itself. So the number or the value of the vector is called the magnitude. The angle is called the direction. So I could say 12 miles at 24 degrees southeast. Here's the magnitude, and here's the direction. A vector has to have both quantities. So on a vector example, you're going to put those quantities there when you're giving an answer. If it's a vector you're answering for. Both of the questions, go ahead.
Okay, so the magnitude is like the distance traveled?
Mm-hmm.
Yep. Can a magnitude be velocity?
Yeah, so like 20 meters per second east. 20 meters per second is the magnitude. East is the direction. So examples of vector quantities are anything that have direction to them. Anything that have direction whatsoever. Now, is temperature a vector quantity? No, it's not a vector quantity. It can be positive or negative, but it's not a directional itself. So certain values we're going to talk about in general are vector quantities. So the ones that we've done as examples, acceleration is a vector quantity, velocity is a vector quantity, and displacement is a vector quantity. Speed is not a vector quantity. Distance is not a vector quantity. If I say how far I've walked, it's just distance. If I talk about my speed in a car, I'm only saying my speed. That's why it's called the speed limit. You don't say, you're traveling 65 miles an hour southwest. You would just say 65 miles an hour. Now, if you're giving directionals and talking about roads, it's totally different. But generally, if you talk about how fast you're moving, you give your speed. It makes sense. Like in baseball, a pitch is 100 miles an hour. It's always directed at home plate. So why are they giving a direction? That's why they don't give a direction. It doesn't make sense to use a vector quantity there. But in boating, it's really important to know the direction you're headed, right? Think about being on a boat. If you're just traveling forever with no direction, you might be on the water forever. The direction matters there. So certain applications, vectors are more important. We've learned 2 ways to look at vectors. The first was graphical. The second was algebraic. Let's take a look at both of those. Let's say we have vector A as the following. And let's say this is vector B over here. And I want you to sum the vectors together. Sum the vectors together. To sum vectors together, we have to think back on what's called tip-to-tail method. We start with our first vector itself. We redraw that. So there's vector A. Same angle you see it at in the original. Exact same angle. And again, that doesn't look exact, but it's close enough, right? And then vector B over here. And then the result of these two, we call the resultant. The result of these two, we call the resultant. And we could put vector symbols above everything if we want to. That's an easy way your book denotes that with little arrows above them to indicate that they're all vectors. So again, this is the sum of A plus B. That's what we're doing in this problem. So we start with vector A, we go to vector B, and our goal is to figure out what the resultant is. Now, graphically, I want you to kind of think of slope. Think of slope. Think of slope. Ready? Look here, please. I would say that the slope of this is like up a couple units, say 3 or 4, if we had a grid line, and over a couple, right? The slope of it is up a few and over a few. That's like your dx and your dy, your delta x and delta y for each of these. So the A vector, I can think of, how did I get to here? I can go in this direction and up, or I can go in this direction and over. Either way is acceptable, right? So which one makes it easier for me to draw? I'm going to draw it to the right and then up, because it's easier to draw. But A could be thought of as going to the right and then going up. But how about vector B? Can I break up vector B into 2 components? Are there 2 components of vector B? What's the deal there, Brandon?
No, because it only moves in the x direction.
Good.
And that's it.
Vector B is only in the negative x direction in this case, or the horizontal direction. So there's no need to break it into components. But any vector that's at an angle, we should always draw its components. Another word for components, it's projections. We should always draw those. Now, if I would like to get from start to end, I could give dimensions here. Now again, graphically, what would you be doing this on? Graph paper, right? So let's say on the graph paper, I'm counting my boxes now, right? And I realize that, you know what? This goes over 3 boxes, right? So that's a length of 3. I'm putting the little spaces as if they're grid lines on the graph, okay? So I count over 1, 2, 3 boxes. That's the length of vector AX. It's X component. The height of that one, let's count the actual lines here in this case. So I've got from here, let's say I'm starting here, up 1, 2, 3, 4, 5. See where I'm counting? From here, 1, 2, 3, 4, 5. So that height of vector A's component is 5. That's that height right there on the right. So this person, this object, this thing that's moving, that's changing its location, went 3 to the right and 5 up. 3 to the right and 5 up. So the actual vector itself means nothing in the graphical approach. I don't even need to know, what is this length here? Well, 3 squared plus 5 squared equals a squared, so I could figure out what this length is, right, if I wanted to. But I don't care. I don't need it. I don't need it. Because my goal is to get over here. And I can do that by going over, up, and then back over, and still end over here, can I? I don't need to take this path. And my goal is to figure out how far I've gone. So let's think about how far we've gone. Well, vector B, let's give it a length. Let's say it goes 1, 2, 3, 4, 5, 6 boxes over. So let's say that vector B is a length of 6. So let's do this physically. Let's think about it logically. I walk 3 to the right. I go 5 up, so I'm at the ceiling now. I walk 6 back over. So I end up 3 to the left and 5 up. And where are those coming from? That's the triangle that makes up R. I end up 3 to the left and 5 up. So again, you have to follow what I'm doing. It helps to see it. If you look at this right now, you're like, wow, there's too much going on. I don't know what this means. We go over 3, up 5. That's the same thing as taking this path. But since we went over 3 and we go back 6, this must be 3. 3 plus 3 is 6. It has to work that way. So the graphical approach, you're literally doing it by inspection, by looking, by drawing it out. On grid paper, it's very easy to do that. So this resultant for R is over 3, up 5. That's what it is. So what does R become? How are we going to figure it out? Well, this is a right triangle. So we're going to use Pythagorean theorem. That's 9, and 25 is 34. The square root of 34 is around 6. It's probably going to be 5.9 something. It's probably 5.9 something. I didn't give units, so I'm not even putting units right here. So that's my magnitude of the vector. What else do I need? A vector has a magnitude and a direction. So how do I find direction? Who remembers? What's the definition of theta? Where is theta always? always one way to remember it. Always.
And or so 0.
No.
The formula you're asking to find?
Not. We're gonna use the formula, yes, in a minute. But where in the diagram is the theta that we're looking at? Like where is theta? Is theta here?
Oh.
Here, 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 or here? We have 9 options. Right, 9 options in these triangles. Where is theta?
It's like between the green and the red
Here?
corner. No, the
Here?
left. Yeah.
Right here?
No. Yeah.
Here?
No. Back to the right.
Yeah.
Yeah.
This angle right here?
Yeah. No. Okay.
Not that one. There's a rule. I had you write it down in your notes. I said the following, so maybe jot this down. The angle theta is always between the resultant vector and the nearest x-axis.
Oh yeah.
The resultant vector is always between, the angle is always between the resultant vector and the nearest x-axis. So, take a look please. Here's my vector right here. My nearest x-axis is right here. The other x-axis, it's all the way back over here, right? I got to go back over 90 degrees to get to this x-axis. So theta is this angle right here. It's always the angle between the vector itself as a resultant and the nearest x-axis. So how do I find theta? I find theta by looking at my components here. Go ahead.
So we do tan -1, and then it's opposite over adjacent.
So what do you got?
So 3/5, or 5/3.
Yeah, 5/3. That's a big difference, right? You got it. So if theta's here, this is opposite, this is adjacent, that's tangent. 5/3 is what tan theta is equal to. So theta is the tan inverse of 5/3. Hey, fun fact. It's not a coincidence that this happens. It happens every time. We actually call 5 Ry, the resultant in the y. 3 down here is really Rx. The formula I told you guys in class, I said, well, this is always going to be Ry. This is always called Rx. And the tangent inverse is always Ry over Rx. You're always doing the tangent inverse, right here. The tangent inverse of Ry, which is 5, over Rx, which is 3. You're always doing tan inverse of Ry over Rx, every time. And this guy over here is always, look, Rx squared, right? That's 3. Rx squared plus Ry squared equals R squared. This is always the same as well. Rx squared plus Ry squared equals R squared. Just like that has Ry, Rx in it as well. So the components of your resultant vector are what matter the most. Getting this 3 and this 5 is the entire point of the problem in order to give us R, this vector length, and theta, the angle. What does that become as an angle? Can somebody give me an approximation so we can write this final answer together?
59 degrees.
59?
Yeah.
Thank you. I don't have a unit for distance right now. Oops. What's my directional in this case? What's my directional? Northeast, southeast, northwest, southwest. Which one is it? Jimmy?
South, northwest.
Well done. Northwest. North is up and west is left. Okay, northwest. I normally would put units after the 5.9. What are the odds? 5.9 and 59, huh? Those are random values we chose. So I usually put units here if we're given units in the problem. If it's centimeters, inches, miles, whatever it may be. Now, this approach that we've taken here for the graphical approach is the basis upon where our algebraic approach comes from. The algebraic approach with the table, where you're adding all the x's together, that gives you Rx. You're adding all the y values together, that gives you Ry. And then we take the exact same approach. So I'm going to go through the algebraic steps for a process like this. And then when we get to the last step, when we have to do this and this, I'm going to leave you to do that piece. Okay? But I'm going to go through the beginning steps for the algebraic approach. So let's start another problem. And let's say that, new problem, okay? Let's say an object starts here, travels 4 miles south, seven miles at an angle of 32 degrees, And then, let's say 3 miles east. Why did I use red? Jesus. I jumped the gun, sorry. Now, what's the overall resultant in this problem? What's the overall resultant from where to where? I'm just going to move that. From where to where? Somebody besides Elias. Overall resultant is always drawn from where to where? Nick? Yeah, it's not a trick question, start to finish. So here's my finishing point at the very end in blue. My starting point is in red. Why is that funny?
I thought it was a trick question.
One thing I don't like about I love this app, but one thing I don't like about it is I can't draw straight lines. Like Notability has that thing where you can like hold down, right, and make a straight line from it. Like take a page out of their book here, jeez. All right, it's killing me. And I just used black, and I wanted to use another color. I got to redo the whole thing. All right, so red is our resultant vector here. Okay, red is our resultant vector. And remember, based on the way that this diagram looks, it looks like we're going to end up southeast. Do we know that for sure? We don't. This is not drawn to scale. I arbitrarily pick numbers. So it's possible that 7 miles actually brings you up far enough, watch please, that this ends up here. And then the vector would have gone northeast. But it looks right now that it's southeast. But we'll figure that out. And the cool part is we don't have to worry about the diagram. The numbers tell us the answer. The numbers at the end will tell us the answer. So let's go ahead and think about this. Let's use our table method to do this. We have x and we have y. We need as many columns as we have vectors plus the resultant vector. I'm going to call these vectors A, B, C, and then R for the resultant, but they don't need a name really. A being the first one, B being the second one, C being the third one, in the order in which they're drawn. R being the result of all of these values. So vector A, the first one here, what direction does it actually angle itself or act? Straight down. What does that mean?
No
Straight
X,
down. Component.
It was
Component.
no X component.
Very good. No X component here. This first distance is 4 miles south, which means that it's only in the y direction, and we're going down. So what do I put? Going down, negative. Well done. And the X component is 0. There's no need, just like with velocity problems, if it's fired horizontally, to break it into components. But if it's ever at an angle, we have to break it into its components. So we've got 0 and we've got -4. I don't like the way that negative is written. How about for vector? I'm going to draw that better. For vector B, how about? For vector B. Is that only the x or only the y this time?
No.
No, it's at an angle. So I have to use my VIX and my VIY notation, the same thing. So VIX, or the r in the x direction, is always the vector times the cosine of the angle. So this is going to be 7 times the cosine of 32. Why is that positive? How come the x is positive? Which way are we moving? To the right, and then up. So both x and y are going to be positive for vector B. And this is going to be 7 times sine 32. Okay? So again, we're using the same exact things that we do to break up velocity into components. The vectors that we learned in the beginning, they come into play a role in projectile motion clearly. Finally, last but not least, 3 miles east. 3 miles east. Mort, tell me about this. 3 miles east, is that only the x or only the y? 3 miles east, which direction are you traveling?
That's on the x.
Yeah, and is it positive or negative from going east, Mort?
Positive.
So I'm going to put a +3 for x. What should I put for y?
-4.
I already have that.
Well,
Right.
yeah.
We got that right here.
Yeah, and 7. Oh, that's +7. Because you're talking about the 7 for the y, right? Oh no, that's x.
So we're only on this one here. Does it go at all in the y direction?
No.
So what do we put?
Oh, then 0.
We put 0 there. We indeed put 0 there. So when an object doesn't move in that given direction, we don't put something in its value. We put 0 in that place. So the 0 goes in for y here, and the 3 goes in for x, showing to the right. Why is this positive 3? Because it's positive to the right. If we were moving left, it would be a negative 3. Now, what we've just done is exactly what we did in the last problem graphically. But now what we got to do is we got to add together all those x's to see how far we move to the right and see how far we move down. So again, we've got to add together this triangle base if we break it into components. We need to take this right here. Take a look where I'm pointing, please. This length right here, which is this, plus this length, which is 3, which is this. Add these two together to give us the result. Why am I not including the first one? Because it didn't go left to right. The first vector only went down. So in the left and rightward direction, I'm only adding the x's together. So let's add straight across. 7 cos 32 plus 3.
I got 8.94.
Now in the y direction, it's a little bit funky because we go down, but then we go back up. So the question is this number more than this number? If it is, we stay up. If this is not as big, we stay down. So what's negative 4 plus 7 sine 32?
Negative 0.29.
Negative 0.29. So our diagram is drawn pretty well. Take a look at our original diagram. Is that not correct? You're getting a different answer? Negative 4 plus 7 sine 32.
I got 1.
You have to do.
Oh, for cosine.
Yep, there you go. Thank you. Good looks.
Yeah.
So what we notice, or you have to put it into degree mode. You're going to say, right? You have to put it in degree mode sometimes if it's in radian. So what we'll notice is this. Follow the cursor, or actually I'll just point. Make it easier. I like using pointers, not the cursor, but I'll do it. So follow the pointer here. This object travels, follow please, 8.94 miles east, and then about 0.3 miles south. That's physically what we just determined. Remember that this is really, oops, stupid highlighter. This is really Rx right there. That's Rx. And this is really Ry, that little height. So if I'm looking at the diagram, that's the Ry value. Just for the sake of getting rid of this, that's the Rx value right there. And there's the overall R vector itself. So what we're doing is we're creating the same right triangle that we created with the graphical approach, really. And our goal here is to find out R, which is the hypotenuse of the red right triangle. The red right triangle. I'm looking there. It's easier, actually, I noticed, instead of having to keep turning around. So the red right triangle we're looking for the hypotenuse of. So we take Rx squared, right, whatever that is, plus Ry squared, and that's going to equal the vector squared. Notice I didn't include the negative sign here only because, what am I going to do anyway? I'm going to square it. So the negative sign doesn't play a role here. Now, even with the directional in a minute, with the angle, we're not going to include a negative sign because we know already that it's southeast. We know it's southeast from the fact that this is east and this means south. Kev, do me a favor. Go close the door to the library. Just the one that separates the library to here. Or Nick. Thank you, Nick.
How do I delete this, Brandon? How do I get rid of that?
The photo?
Yeah.
Oh.
Oh, no.
Delete it or not?
No, you're good, you're good.
He told him I was getting mad.
Yeah,
Good.
yeah.
Good.
Represent.
So our goal is to figure out this R. Thank you, Nick. To figure out this R value, this vector length. But we also need to figure out the angle. The angle is a little bit tricky here to find. It's that little angle up here. Here's the angle right there. That's the one we're looking for. Remember, the vector and the nearest x-axis. The vector and the nearest x-axis. So the angle theta is that little angle in there. I'll try to draw it in there small. That's that angle theta right there. So theta, go ahead. Yeah, but if you look at this, right, and as you do it more, if you're good at this, would you be drawing all the stuff in? No, I'm teaching
No.
you. So I would not be drawing every single thing in if I'm doing the problem. Now, if I'm not comfortable, maybe I do that still, and that's okay. But as you do more of these, as you practice more of these, as you should have been and maybe do more tonight, you get to the point where, hey, put it right into the table. Get these values. You're always squaring them. You're always taking the square root. You're always using the tangent. It's the same problem over and over. I can't change it any way to make it harder. It's physically impossible for me to make this any harder than it is. It's the same problem every time, just different numbers. So tan theta in this case, Christ almighty, I'm just loud, huh? Is ry over rx. I told the last class that they maybe want to, nice, somebody closed it. I told the last class that the absolute value signs are really important there, because when you take the tangent inverse of a positive, you'll get a positive answer. The southeast, again, is what's telling us where it's going. So what do my numbers turn out to be for these parts?
-1.85 or 1.85.
Theta is 1.85?
I think so, yeah.
It's a very small angle, I know that. It's going to be a light angle. What's the R value turn out to be?
I think it was 8.94.
So your final answer should be written as 8.94 at 1.85 degrees south of east.
How did we get 8.94?
That's what I just heard from you guys. You said that this was 8.94. It didn't really change.
Oh, okay.
Nice. How'd you get the angle? At the end, I put in 10.
Negative tan inverse.
Of 0.29.
Inverse?
Yeah. So second.
Oh, okay.
Hey, quick reminder.
Yeah.
Under documents and handouts, there are about 10 projectile motion practice problems. Thank you, sorry. There are about 10 projectile motion practice problems under documents and handouts with solutions fully written. It's to your best interest to practice. Do it yourself and then look at the solutions. Don't just read solutions. It will do you no good to read solutions alone.
What's it called?